So let's get started, and now we're going to do an example. So this might be interesting for you. So in the on the bhacker.com website, if you want to download the PDF files that go along with this example we're going to go through, we're going to go through the first half of the example, build an entity relationship diagram, and then translate the diagram into a bunch of tables. So I'm going to flip it up a little bit. We'll do a hands-on exercise. Then we'll go through how to translate, and then we'll translate with the same exercise. So in order to find this exercise, go into the Oracle database part of the Summer 2013 Oracle Database Management Administration. And then in the bottom where it says Previous in-class exercises, you guys will be lucky. Last time I made everyone do this in class, and then I discovered that when we broke for the in-class exercises, everybody left. So now we're not doing it. Instead, we're going to do them as a class together right now. So it breaks it up a little bit, allows you to think a little bit. So what we're going to do, we're going to skip exercise 1 and go into day 2 where it says entity relationship diagram exercise. So this is the one here, this day 2. These are on dependencies. You can go through and look at the dependencies if you want, but the dependencies are kind of old. We're not going to do dependencies in this class. We're just going to do entity relationship. So go ahead and click on this one here. This is the solution. Don't peek at the solution until we go through, or actually I'm going to peek at it. I'll show you the solution. You can peek at it if you want. But it's a nice little before and after exercise to put the pieces together. So I've already downloaded these items, and they are on my desktop right here. So this one here is the entity relationship diagram. This is the problem. So customer comes to you. Imagine, so think out of the box a little bit. Now you're a database architect, and you're going to design the system. A customer's come to you and said, hey, I like to build a database to store and manipulate information about movies. Okay, and each movie I'd like to show the number of movie stars that participated in the movie and the studio that produced it. Okay, and once the project is complete, I'd like the database system to answer the following questions. No one's going to come to you and tell you this. This is made for illustrative purposes. Instead, they're going to say, I need a movie database. And in the movie database, what do you want to store? You're going to ask questions. Well, you'll probably be asking these questions to get these answers. So this is made for easy. This is easier than assignment number 1. This is made for easy translation. So what we're going to do here is we're going to take this and create some entity relationship diagrams out of it. So the task is to create the entity relationship diagrams from the textual description, exactly what you'll be doing in assignment number 1. And then the second part, which will continue after we start the lecture again, so we're only going to do part 1 right now. Second part is to take the database, create the database schemes, the tables from the entity relationship diagram so we can see the big picture. But we've gotten this far already, so we can take it this far. Now, instead of spending the next hour or 45 minutes or so going through this, because the first couple of times you do it, it will take you a while. But on the top of my head, I can probably start thinking about entities, and they're generally the nouns. And then the participation and the relationships are generally the verbs. So then I can sort of see how this works together. If you're not an English person, that doesn't make any sense to you. But if I were to look at this and say, I'd like to build a database. All right, you're not telling me very much about the database. We're just going to build a database. So store and manipulate. So we're probably going to call the database movies because it's about movies. And then for each movie, you want to know the movie stars that participated in that movie and the studios that produced it. So I'm going to have a movies entity. I'm probably going to have a studios entity. I might even have a stars entity. So if I take a look at the solution without going through the labor of actually doing it, then I guessed correctly. I have movies, stars, and studios. So the first thing that I would do in this particular case is draw these out. This one was written by hand actually, and I put these are the attributes, by the way, and I stuck the attributes in bubbles around the movies. This is a very old-fashioned way of doing it. If you're doing it by hand, this is probably better syntax for you. This, however, is not the most, as I was mentioning before, it's not the most efficient because this is going to create an extra table for us. But I wanted to create the extra table because I wanted to give you a better example in terms of translating those tables, what we're going to see. But this is really three entities that are participating together because aren't movies produced in studios with stars? Don't the stars participate in this relationship? And doesn't this relationship participate in that one? How can you make a studio in a movie without stars? The stars are the actors that are acting in the movies. Don't you need the stars in a movie? Don't you need the studio? Don't you need to be making a movie to have the stars at the studio? So all three of these are really all in one. And do I have a paint program on here? I don't have a paint program on here. If you were to imagine this with movies here, stars here, and studios here, this is a three. These are three entities all participating in the same relationship. So instead of drawing it like this, I could put them together, and the stars and then it produces is really one relationship. But this is the more typical way for beginners to draw it out, because they're going to read it line by line out of the description. So let's go back to the description to see what we're talking about then. So for each movie, I'd like to know the movie stars that participated in that movie and the studios that produced it. So that's where I get movies, and I have stars that star in movies, and then I have studios that produce movies. So I've taken that textual description and I put it into a picture. And so now I'm going to go back here and take a look. Once the project is complete, I'd like the database system to answer the following questions or queries. None of the time are you ever going to have a customer tell you this much detail. But if I were to answer these questions and perform these queries, this is where I'm going to get my attributes from. So tell me the black and white movies which were made between 1930 and 1950. Well, wouldn't I need the date and the color, or black and white? So on the movies end, I have color, and then I have year, actually. So then I've got attributes coming out of that. So one of the biggest things you're going to get is when you read the descriptions for the 3 or 4 scenarios that you're going to get assignment number 1, you have to decide, well, is it an attribute, is it an entity, or is it a relationship? That's why I go back to this noun-verb kind of thing. So studio, movies, those are nouns. And the verbs are like produces, stars, ends. Or are they adjectives? I don't know. I don't know English too well. They're not nouns, I know that. So they're describing the relationship. And then these are more like attributes. But if I gave it, I said date. So it could be date, but it really, is it the date or is it the year? So over here I could probably have put date instead of year, which is what you're going to do. Well, I would have done it differently. I would have put year here. I would have put date instead of year. And then I know more than a year. Well, what if I wanted to know the month? You know, what about everybody that was produced a movie in the month of April or something? I wouldn't be able to get that if I'm just storing the year. So it'd make more sense to put the date in there. So then it says here, tell me the movie names produced by Studio Fox that feature Tom Cruise. So the studio, here's the studio, probably their name. Now you probably could have put first name, last name, Tom Cruise, instead of Tom something else. Huh? Oh, stars, I'm sorry, stars. Names up here too. And then studio has a name, but yeah, the stars names, and then we have the studios down here. So we have the name of the studio, but we also have the name of the star, Tom Cruise. So what did the question say? It says, tell me the movie names produced by Studio Fox, Studio Fox, that feature Tom Cruise. So here's the movie names that are produced by Studio Fox. So Fox is the studio, produces movies it stars in, names the stars Tom Cruise. So it's not what I'd call a direct translation from textual description to diagram. There's an art to it. There's a way of thinking, and it trains you actually, going through this exercise actually kind of trains you to think like that in terms of how you're going to put the data together in terms of its relationships. Which female stars participated in more than 3 movies? Well, these are queries that you're going to run. So in the stars, you probably want to put gender, maybe. So we have gender now in the stars database. You can download this one. It's called The Solution. There is no key for it. It opens up. There's no password for the file. And then birth dates, and then, what was it? More than 3 movies. Well, we have the stars that star in movies. We can count up how many movies there are with a query. And then we have which female stars, which studios produce movies featuring Nicole Kidman. So which studio produced movies? Well, then we have studios that produce movies that star in Nicole Kidman. We can get that information out. So in kind of a reverse way, actually one more here. Which movie has the longest duration? Well, I'll put a duration on the movie. So here's our movies, and now we have a length. So we have length up here. So what generally happens is you get this description. It says, I need to keep track of, let's say, go back to university as an example. You know, university ITU needs a database. Well, what do you want to keep track of? And then you start coming up with all, well, okay, we need to keep track of how many classes students have taken, what they registered for, what they paid for, when they're going to graduate, what their GPA is. And then you have this whole big old list. It usually comes in the form of a requirement specification. Database architecture takes this list, draws this diagram. Or not this one, but one similar to it, based on that list. And then you start asking it questions. How many classes has the student taken? When is the student going to graduate? Has the student graduated? You know, then you have status, GPA, and it gives you all the little attributes to fill in, which is helpful actually. Because then you have to figure, you know, do I want to make color an entity? No. Color, black and white, that's an attribute. And what's an attribute of? Well, it's an attribute of movies. So rarely are you going to get something this simple. It's going to be a little bit more complicated. It'll be like the drug manufacturer produces drugs, and those drugs get used in products. And those products, so to go back a little bit here, if we take a look at the, oops, I didn't download it. If we take a look at the exercise 1, actually let's take a look at exercise 2. Exercise 1 is just writing a memo. There is a solution. The Oracle rules is the Oracle rules, or Oracle rules. It's written underneath there. This is the description for it. And in here, as an example, I'll just take a look at the first one. This is another exercise that you might want to go through. This is the dependency diagram, however, so we're looking at the arrows that are here. And the solution actually has oh good, the solution actually has the questions in it too. So the questions are in part of the exercise. So number 1, doctors prescribe drugs for patients. So we have doctors and patients here. So the symbols look a little different because this is a dependency diagram, but you can sort of see how this comes together in terms of the relationship between doctors and patients. I would just put a line here and put prescribes next to it. And then doctors, many doctors can treat a patient. So doctors with patients, well then that's cardinality. I'd add that in there. So you're just putting in the number of participation. Many doctors can treat a patient. Many doctors can prescribe the same drug to the same patient. So doctors prescribes drugs to the patient. So as a dependency diagram, this works. As an entity relationship diagram, this is pretty lousy. Why is it lousy? Everything's an entity, there's no relationships. So isn't prescribed sort of a relationship? So on dependency diagram theory, we're not looking at very much. We can't show the same level of detail. In dependency diagrams, they don't translate into database tables too clearly, which is why I kind of skipped this one, because we don't necessarily want to deal with it. But if we see this as an entity relationship diagram underneath it, this is the same scenario. On the top, we have the dependency diagram that doesn't match anything that we just went through. But we look at this down here, we look at the entity relationship diagram. Now we see the relationship. Now prescribes turns into a relationship. And now we see that we have doctors that treat patients. And then we start reading stuff, and then we say, well, patients involve prescriptions. Do they really involve prescriptions? Well, they sort of do, because they're prescribed by doctors. So we could have turned prescriptions into a 3 relationship. And I'm just showing you different options right now, not to confuse you, but to show you that you have some creativity in terms of how you put this together. We could take doctors, prescribe, to patients, prescriptions, and turn this one here, which is really a 3 degree. We have extra relationships going on. So this could have been doctors treats patients, doctors treats, but they also prescribe, and they're involved with prescriptions. And prescriptions include drugs. So do drugs part of the doctor-patient? No, prescriptions are, because doctors and patients prescribe prescriptions, and prescriptions are drugs, technically. So anyway, that's here's car parts. So this is a longer one. Let's see. I think the last one's actually shorter. No. Anyway, if you want more examples, you can go through here. You can see the dependency versus the entity relationship. But I don't require that you know anything about dependencies for this course, because in the past I've tried to teach the dependency stuff and I realize it's too confusing. If you can get through the entity relationships, you're in good shape. So, after we create the tables, after we create the diagrams, the final part of this is to create the tables. Now, there's a kind of an easy step-by-step approach to take to translate the tables. The tables are going to be formed from your diagrams. So you're going to read the diagram to create the tables. So in designing the tables, first approach is to draw the dependency or the entity relationship diagrams. Each statement is a single path through the diagram. And the tables are formed by traversing the dependency diagram. Simpler method is ERD diagram instead of entity relationship. The paths are hard to follow in a dependency. It's much easier to follow in an entity relationship because we have the relationships mapped out for us. We transform the entities into tables, we transform the relationships into keys, and then you're done. No paths to follow. So here's our starting diagram. So let's take a few minutes and look at the starting diagram so we can see what we're starting out with. Employee, and okay, so the slide here is kind of odd. Don't worry about the dark versus the light lines. They're all just the same quality lines. These are the relationship symbols. We have an employee, and we have 3 relationships that he has. And we also have a recursive relationship. So this is the employee that supervises, so it's the staff member that is also a supervisor. And this diagram is drawn, well, it was originally drawn by hand, so the attributes are in little bubbles outside. Some people like this, some people don't. I actually kind of like it this way because, well, it doesn't look as confusing, but there's more things on the diagram. The tools nowadays will all have you put it inside, so you won't see the bubbles out here. If you want to put bubbles out there, go ahead and do it. It works just fine. There's no reason why you can't do it. So if you remember the employee, we have a 1 to any number. So we have to have at least 1 supervisor, but we can have any number of supervisors. And they're all employees, so it's recursive. Employees work for departments. Employee manages departments, and employee works on projects. Projects are controlled by departments, or departments control projects. And then we have the employee that has dependents, and the dependent is the dependent of an employee, and so we have a weak attribute down here too. Oh, excuse me, a weak entity down here as well. So let's see how this works together, and we'll revisit parts as we go through. The first thing I want to do is review the key constraints, making sure the arrows are pointing in the right direction, because the arrows are going to determine, when you read it, which entity is going to pick up attributes from the other entity or from the relationship, one or the other. So an employee can work in many departments. Okay, a department can have many employees. All right. So in contrast, each department has at most one manager. So according to the key constraints of manages. So we fix the management. So this is S's scroll wrap is wrapping on us. So this is manages, this is employees, plural. So we make sure that the key constraints are correct. And the constraints are the number of participating entities that we talked about. Then we review the participation constraints. We're just checking the diagram at this point. These are good checks to do before you start translating, because once you start translating, it's hard to go back and fix the diagram. You have to translate all over again. So does every employee work in a department? If it does, then we make it mandatory instead of optional. So we're never going to have a 0 there. We're going to have a 1 or 2 or more. So if so, this is a participation constraint. Basically, it means at least 1. So we have to make sure that we're keeping that intact. And then identify the weak entities. Well, why do we want to do that? Because we have to make composite keys with the weak entities. If you remember that composite key discussion we had. A weak entity can be identified uniquely only by considering the primary key of the owner of the other entity, or the owner entity, which is the entity that controls the weak entity. So the owner entity set and the weak entity set must participate in a one-to-many relationship set. One owner with many weak entities. Think about the dependents on the employee health insurance policy. Weak entity sets must have a total participation in this identifying relationship set. There has to be total participation instead of partial participation. What does that mean? If you're going to list an entity as a dependent and he's going to be in the system, then don't list him unless he's going to be on the health insurance policy, because you're assuming that everybody in there is. So you take them out. So they're not in the system unless they're part of the system, which makes them required. So weak entities have only a partial key, is a dashed line here. So we put the dashed line in the diagram to determine that from the policy of employees that these are dependents, these are weak. Lucky for you, in your first, actually all of the assignments, none of them have any weak entities in them. So you don't have to worry about your weak entities actually, because I left it out. Because that confuses a lot of people, and there's only rare cases in which the weak entity turns up. And for the most part, the weak entities are treated just like the strong entities, except for that composite key. But a lot of people get confused with that, so let's leave it out. Here's some relationship reviewing, bad design versus good designing here. So if each policy is owned by just one employee, the order, remember those two problems we ran into before we took the break? The problems with the relationship diagrams. So there's one that exists in here, so we have a ambiguity, so we can correct the ambiguity. So the bad design is up here. The good design connects the weak entities correctly and creates the beneficiary of the dependents. So key constraint on policies would mean that policy can only cover one dependent. Not such a good idea. We want it to cover multiple dependents, so we can change the key constraint around. So. And then the last thing you want to do is review the relationships. We still haven't started translating it. We're still making sure our design is good. So take a little note and make sure your relationships are good. In the previous example, illustrated the case where the two binary relationships were better than the 1-3 relationship. Sometimes you have to take the 2, put it into 3, take the 3, put it into 2 2s or something, so you can review that. An example in one other direction is the 3-degree relationship contracts. Relates to parts, departments, and suppliers. As description, quantity. No combination of a binary relationship is adequate substitution for that, so you have to make it into a 3. Sometimes the 3-degree relationship is a requirement, and sometimes you can't get away with a 2 2s instead of a 3. And it's not like a direct translation where you can take a relationship and change it around at will just to make it binary. Not everything translates that well. Here's an example as well where we've got a 3-degree versus this is a binary. So just to review the concept, this is a binary, only one relationship with one. It's a circular binary. This one here is a 3-degree. This is a attribute quantity on a contract. So parts have a contract with suppliers and departments, and there's a quantity that's a part of the contract relationship, is an attribute of that relationship. Versus here, where parts needs departments that deals with suppliers that can supply as parts. It's a binary and a circle. So if you ask the question to yourself, can S supply, supplier can supply P, D needs P, and D deals with S, does not imply that D has agreed to buy parts from S. So this gives you that lack of connection, so it's ambiguous. So sometimes it's better to create the multiple degreed relationship, long story short. So let's revisit. This is what the original looks like. Now we're going to start translating. So step number 1, each entity becomes a table. So if you can remember, write down step number 1, take all your entities, turn them into tables. How do you define the tables? Well, you can define them this way. And how are you going to document them, I should say. You don't have to write SQL code for it. Some people do them in sets. They'll go the name of the set, employee, leave out the entity name, maybe just to say employee, and then list out like in a set, separated by commas, all the attributes. So in this particular case we have 3. We have, and they're in purple here, employee, department, project, and dependents. But we left out dependent because it's weak. We're going to deal with them separate. So we have employee, department, project. That's the entity turned into employee, department, project. You don't have to use the same names, and you don't actually have to list the entity that it came from. Just create your table list. So when you're done with the entities, you can cross them off the list. You don't have to worry about them anymore. They're all done. It looks like it's attendance time, so we're going to pause the video shortly here. I'll pause capture. Alright, so we take the, just so we can pick up where we left off for people who are in this audience, we're going to take this, we're going to translate this entity relationship diagram into a bunch of tables, which is the goal of doing this, which is the reason why we're doing this. Alright, so each one of the entities turns into a table, and then we can identify from the diagram the list of attributes that belong in each one of the entities. In the diagram, we have underlined candidates, which means here for department, we have department name, department number. We have different things. At this point, when we create the tables, we need to identify the primary key. We pick one. So we pick one primary key out of here. So if we were to pick employee, we've decided to pick employee social security number, and we have social security number over here. We can call it something else. We don't have to call it what we called it in the diagram. We don't have to call the table the same name as the diagram, but the closer we get, the more we can remember what we did. So if we're taking a systematic approach, we've done all the tables out of the entities, and at this point all we're doing is identifying primary key. We can always add the other attributes to it later. And some people like to take it at this point, add the attributes to it. That's fine as well. After we get done with all of the entities, then we start looking at the relationships. So we have the 1 to n, 1 to any number or many relationships. So we can create the primary key from the relationship. So in order to get the one to many, we have to create a key. So for the one to n relationships, we create another key. So we create a primary key from the entity on the one side. Because there's only one of them, we don't need a separate relationship for it. So on the one to many, we take the one side, that's the one, we create a key on the many side. So the table that's on the many side has a one attribute that's associated with the relationship. So this type of relationship with the one turns into an attribute or a column. So we have and it's a key column. So we create a primary key from the entity on the one side to the entity on the n side, where it becomes a foreign key. So employees is the n, department is the one. So employees, any number of employees work in the same department, but employees only work in one department and it works for. So department number is moved to the employees entity. Which department do you work in? If you only work in one department, then all we need is the department. So the department number in the employee table. Then we examine the weak entities and we treat them the same. We treat them just like the regular entities. So the dependent entity cannot exist on its own and must have a parent entity. So dependent works with parent, which is the employee entity. So they are identified by the many-to-many or many-to-any number relationship, and they intersect entity with the primary key as the composite of the primary keys of the two or more other strong entities. So what does that mean? If we take a look at it here, we have the weak entities that become tables as well. So for each one of the entities, you create a table of the weak. So that's why I say some people don't specify weak versus strong, because an entity is a table anyway. So we don't necessarily have to designate it as being weak or strong. Knowing that it's weak helps you to remember that you have a composite, because here's your composite. Your composite is the employee social security number with a dependent number. If you don't create the composite, you lose the weak relationship. So you include a primary key of the owner tables, so the employee table who owns the dependent. So the primary key becomes the owner key plus the weak entity key. So here's the owner key, which is the employee social security number, and then the weak entity key, which is the department number. And the table is going to be called dependent. And this plus is scrolled. So this is employee social security number plus dependent number. That's the pluses over here. It kind of scrolled on the slide. So what about the many to any number, or many to many relationships? They become tables. So for the many to many relationship, you create a new table with the primary key being the primary key of both entities involved in the relationship. So we have employees that work on projects. So we have an employee number, we have the number of hours, and then we have the project number. So this is a composite of project primary key, employee primary key, along with the attribute for the work on relationship. And the works on is how many hours. So employee E1 on project P1 worked 3 hours, and employee E1 on project P2 worked 4 hours. And then we have the employee 2 and employee 3. So we can keep track of the number of hours. So the multiple relationships turn into tables, the single value doesn't. The single value is just another attribute that's being added. So in terms of this, if we were to take a simpler diagram on the left-hand side, translate it into one on the right-hand side. So on the left-hand side, representing the many-to-many relationships in the ER diagram, this is a many-to-many. And I want to tell you a little bit about the crow's feet in this particular example as well. These are attributes. This is the entity. The 3 here is saying that it's a many. That's called a crow's feet syntax. You'll see a lot of that actually in most of the tool sets. They favor the crow's feet. The 0 or the 1 is optional versus mandatory participation, which is kind of the tricky one there. So it's multiple with, you might have an order. Are you going to have a request for a product? Well, usually would. Or it might be back ordered. May not be a current request. Might be a recurring order. Requests for products you're going to have multiple products on there, but you have to have products in order to have a request for the order. But you may not have, it might have an order in the system, but it doesn't have anything on it. So we have order number, order date, promise date that are attributes associated with the order entity. Many orders might exist, and on the order we have the request. And the request has a quantity, and this is the quantity ordered of the product, and the product is product ID, a description, a place, maybe some other attributes associated with it. So if we look at the table translation that comes out of this, we have order, order line, and product. I don't know if I would have called that order line. Order looks pretty clear. Products looks pretty clear. You could call it requests, or I don't know, order line. Yeah, I guess it is order line. So here we have the order number for each one of the orders, the date, the promise date, the other two attributes. And then down here we have the product with all of the product attributes that are associated with it, and the product ID is the primary key. And then the order line, because this is a primary key in the order table, it's now a foreign key. So it's called a foreign key in the order line table. And then for the product table, we have product ID, which is also a foreign key. So these are order numbers, a primary key. We have two foreign keys. We don't have a primary key in the order line table. We don't need one. It's a relationship table. So relationship tables don't normally have product IDs, but I see them all the time, or excuse me, primary keys. But you see them all the time. You see order 1, order 2, order 3. They'll put in an order. Why do you want to do that? Easier to search on, maybe. Who knows? So you've taken this out of third normal form and you put it into second normal form by adding a primary key, because you put a candidate in there that was unnecessary. So usually they'll put in something for some reason, but you don't actually have to. This would be like a classes table. Do we need to know how many classes? Do we need to search on classes? No, it's a join table, and when we're running the queries on it, and we're going to join it because we're going to look at the order number, come up to the order number and see what number it is. It's 61384 right here. And now we're going to get the information that's associated with it from the order number. And then the product ID, we're going to get, it's a bookcase from down here for this product ID. And then we also have we also have a wall unit that's part of this one too. So that's basically the translation as it moves over. If we were to look at multi-valued attributes, which is the last thing, so we have the relationships that are single versus multiple valued relationships, cardinality. Then we have this concept of multi-valued attribute. A student takes classes. Well, how many classes? They take more than one class. That's a multi-valued attribute. For each one of the multi-valued attributes, you create a new relation. So for the multi-valued attributes, you're creating another table, and that table is going to have the primary key is the primary key of the entity plus the multi-valued attribute. So if it's department at multiple locations, then we have the table that's called department locations. And we have department and location. And so we have department 1 at two different locations. So we can list out the locations. So if we had this for students, it would be student in the student table, and then we have registration table. Registration table has student D1 took this class, student D1 took that class, and you'd have a multiple entry for each one of the classes for your multiple valued attributes inside of the registrations table that would show each one of the classes associated with each one of the students that was taking it. What about the n-array relationships? Any number, for example, for the n-array relationships, you create a new entity and create the primary key of each entity involved in the relationship with the new entity. As an example, supplier supplies parts for cities. We didn't have one of these. We didn't have one of these either. So we were going for a different example. We didn't have one of those in the diagram. You're not always going to get all the cases in each one of the diagrams that you put together. So here we have suppliers that supply parts from cities. So we have here we have the table supplier parts cities, which is kind of a combination of all three of them. And then we have supplier number, part number, city. So we know that supplier 1, S1, has nuts that come from 2 different cities. Just like car parts. You know, they come from same car parts, got different cities for different parts for different suppliers. So here's our finished table design. As we look at it, we've got, if we took the tables that we created and merged them in with an entity relationship diagram, this is a combination. You're never going to see this. This is the tables written out with an entity relationship diagram. So we have the employee entity that has a primary key here, a social security number. That's a multiple degree relationship. We have departments, but it only works in one department. So we have a optional, well, it has to work in one department. So with a foreign key here, and then we have the department number. So this is a kind of a hybrid cross between an entity relationship diagram and a table list all put together. But this is the finished list of tables. If you can read through all of this chicken scratch that's on here, it's the completed list of tables that are associated with that original diagram. So what you have to do is sort of go through it in terms of a methodology. And if you take it step by step, the first step is you're going to translate the entities. Second step, you're going to look at the relationships. And so if you treat the weaks and the strongs together, it's all done in the first step. But make sure on your weaks you're making a composite key for the primary key, so it's both the employee and also the dependent number together. Just remember on the weaks you have to create that strong relationship out of the week. You have to merge it. So starting with the entities, deal with the weeks, then go into the relationships and figure what kind of relationship is this. Is it a single valued relationship? One student takes one class. If it's a single valued, no table. Instead you move the class into the one, you move the sides together. So that becomes an attribute instead of a key. If it's a multiple, you take the relationship, you turn it into a table. Then you take the table and add in a foreign key, so you can link both sides of the table together. So you have 2 foreign keys in there, along with whatever data is associated with that relationship. And then you progress through until you run out of entities and run out of relationships. Some people like to start at one end of the diagram and work their way. Some people just like to start with all the entities and then start with all the relationships second. I'm more for getting rid of the entities than get rid of the relationships and then dissect it down. Which is actually kind of simple if you think about it. It's just remembering you have to tie it together. So each one of the tables needs a key of some sort. It needs a primary key. So if we look at the second part of that solution of the entity relationship diagram that we looked at with the movies, we can translate this as another example here, simpler one, and we'll see, because we have multiple relationships, if we take this and translate it as is, without combining the relationships, we're going to have an extra relationship. So if you don't take it out here, you got to take it out when you work with the tables. So convert each one of the entity sets into a relation, and then use the attributes of the entity set as the attributes of the relation. So the attributes go in. Also convert each relationship into a relation as an attribute we have for the keys that are connecting the entity sets. And the keys of the many-to-many relationships, the stars in and the unions of both keys. And then for the case of the many-to-one relationship produces, the key is only the key corresponding to the many side. So just to review the concept here, we have movies, stars, and studios. So I have movies, stars, and studios. The first 3 I'm going to do here. And here I made bold the primary key attribute. So sometimes in the diagrams, people like to mark it in the diagrams. I don't actually like to mark it in the diagram. I'd rather mark it in the table set, because maybe I haven't decided yet. Plus, then you're thinking ahead and you're writing the table structure before you finish the diagram. So if you take it in this order, you can use this syntax, and you can use it in your homework assignment as well. Looks like a set. It is a set. Movies is the title, year, the length, and the color. Stars has got that, Studios has got that. And then next you see the two relationships, stars in and produces. So you have 1, 2, 3, 4, 5 tables that come out of that. But you've got too many tables. How do you know that? Well, you can simplify the model and you can eliminate the relationship between the many to one relationship with produces by adding the attribute studio name to the movie's relation. Because if you look at the two relationships, we've got movie title, movie year, star name, movie title, movie year, studio name. So it's easier to see how you can combine these two together by moving it. So if you moved movie title, movie year, movie title, movie year, these two are the same. So you could take studio name and move it up into stars in, and get rid of produces actually. So we can have the movie name, star name, movie year, and movie title, and then studio name ended up in the movies. So we got rid of studio name because the studio name was the relationship here that actually should have been part of the 3. So if this was originally connected to stars in, we wouldn't have the produces. So you can possibly see how 1, 2, if I drew it this way, put stars in right here, get rid of this here, it would have been the same thing, and it actually would have been clearer. So if we do it this way, then we have to go through the process of eliminating, because we have one too many tables. Because this is a many-to-many, this is a many-to-many. We didn't put the many-to-many, we didn't put the cardinality on the diagram, but we could if we did. Many movies have many stars in it, unless you just have one movie with no stars in it. We have some cartoons, but even though they have voiceovers, they have stars in them. And many stars work in many movies, because you're not going to be a star if you only moved, one-hit wonder. You only performed in one movie. But you can't make a movie with stars without studios, can you? You got to have a studio. It has to be produced somewhere. So that's why produces and stars in is really the same relationship. But the produces is connecting the studio name. So you move the studio name out here, and you move it next to the studio movies. Actually, movies makes more sense to move it in movies. And then this is really a 3-degree relationship, not 2 binaries. Usually when the students start out to do this, the first thing they're going to do is create binaries for everything. So don't be afraid to make a 3-degree relationship, because it makes this process easier. Now, for the purposes of the final exam for this course, what I did last time is I gave you a textual description, and I had you guys draw, well, I didn't have you guys, I had the last group draw diagrams, and then we took the diagrams and we translated it into tables. Funny thing is I noticed a lot of people, I'm probably not going to do this again, although I probably could, I don't know. But you already know, because I'm going to tell you what everyone did, is they did it backwards. They guessed at the tables, then they drew the diagram to match what they guessed at, and the diagram didn't make any sense. So that was a lot of points lost, actually, because if you did this table set matches this, actually. Because it's not only the same, but it's showing you the relationships. And it's showing you the way it's put together. So the stars and then the produces is the sort of unique part of this. If you were to give me this set, this is technically correct, because you have stars in and you have produces. But what ends up happening is people won't name it stars in or produces. They'll come up with these other names, because they'll take a look at this, not consider the relationships, instead just consider the entities. So 9 times out of 10 you'll come out with 1 or 2 tables, 3 tables maybe, and they'll be guessed at. And so you'll figure out, well, and then you draw the diagram, and the diagram doesn't match the textual description normally. So it's like a red flag. It's easy to see it. So. Questions about entity relationship diagrams? No? Alright, I'm going to end this one because this one was on entity relationship diagrams.